Today's lesson will explain how indicators and buffers work. The principles of equilibrium can be used to explain how indicators work. Instead of one chemical, indicators are two entities. These two entities are a Bronsted-Lowry acid-base pair. The two different entities will have different colors, so the solution will have the appearance of the entity that is acidic or basic. Phenolphthalein is a commonly used indicator that is colorless when in acidic form and pink when it is in its basic form. The indicators that we will commonly use have very complex molecular structures, so we will typically use a shorthand to identify them. In the case of phenolphthalein, HPH is the acid form, and pH- is the basic form. When an indicator equilibrium is shifted to the point where equal concentrations of both forms exist, you may observe an intermediate color. Bromothiamyl blue has a green intermediate color at a pH of 6.8. This equilibrium equation and Le Chatelier's principle can be used to explain how indicators work. HIN is used to represent the acidic form of the indicator, and IN- is used to represent the basic form. You're going to notice that the acidic form usually has an H, and the basic form has a negative charge. What do you expect would happen if additional hydronium ions were added to this equation? According to Le Chatelier's principle, adding hydronium ions would cause the equilibrium to shift to the left. This would result in more indicator in the form of HIN, which is the acidic form, being produced. What do you expect to happen if hydroxide ions were now added to this system at equilibrium? Hydroxide ions would react with hydronium ions, which would effectively remove some of the hydronium ions from the system. So when they react, they just form water. This would result in a shift of the equilibrium to the right and an increase in the basic form of the indicator. Different indicators have different acid strengths, and so the pH at which indicators change color can vary. The pH values for different indicators is listed in your data booklet on page 10. Notice that indicators have Ka values just like the acids and bases in your acid-base table. Buffers are mixtures of conjugate acid-base pairs that maintain a nearly constant pH when diluted or when a strong acid or base is added. Buffer solutions have specific pHs that are a result of the entities that are used to make them. Buffers have special properties in that they resist pH changes when acids or bases are added. Bronsted-Lowry equations and Le Chatelier's principle can also explain how buffers work. In this case, an acetic acid acetate ion buffer is used. The result of adding a small amount of sodium hydroxide is observed. To determine the expected reaction, list all entities, and then use the strongest acid and base to write the balanced equation. This equation shows you that when sodium hydroxide is added to the buffer solution, the hydroxide ions would convert a small amount of acetic acid to acetate ions. The result of adding a small amount of hydroxide ions on pH is reduced by the buffer solution. The pH will increase, but very slowly. This titration curve shows that there is a region where the solution is buffering effectively. The same solution that buffers for bases can work equally well if a strong acid is added. Here, HCl is added to the acetic acid acetate ion buffer. Entities are listed, and the strongest acid and base are identified. The addition of hydronium ions and HCl would result in a slightly higher ratio of acetic acid to acetate ions. The pH would lower, but not as much as if the HCl was added to water. Buffers will only resist pH changes for so long, though. Ultimately, enough of a strong acid or base can be added so that the pH will begin to change very quickly. Buffers are extremely important in many biological processes because certain chemical reactions can only occur at specific pH values. For example, some enzymes work most effectively at specific pH ranges. This makes buffers such as carbonic acid and hydrogen carbonate ions very important for metabolic functions. Buffers are also widely used in different commercial and industrial applications. The production of antibiotics and cheeses must occur at specific pH ranges, so buffers are used to help maintain these values. This is your second last video for this unit. Be sure to ask any questions that you have about this theory-rich lesson in class. The unit test is coming up very quickly.